So welcome everybody to this inaugural lecture. My name's Jim Watson. I'm director of the UCL Institute for Sustainable Resources, and I'm very pleased to be introducing Professor Paul Dodds, my colleague Professor Paul Dodds, to give his inaugural professorial lecture. Paul today is going to talk, as it says on the screen, about energy system modelling. What has energy system modelling ever done for us? I was just asking Paul how long he'd been at UCL, and the answer is just about almost 11 years. He's a professor of energy systems here and works on research spanning the boundary between economics and engineering. And as his talk title suggests, he's spent a lot of time focusing on the development of use of energy system models. These aren't just models that are used in academia, but increasingly, for a long time, they've been used in government, including in the UK government. And he particularly focuses on the UK Times model. That's a model for thinking about long-term energy system change, and particularly, for example, how we might meet our climate change targets. In his work, Paul has focused on a whole range of different energy sectors, but particularly on hydrogen over the last decade. So I think he's going to talk about that as part of his lecture. He's also working at the Research Policy Interface. So, for example, he co-chairs a Standards and Regulations Working Group of the Hydrogen Advisory Council for BEIS, the Department for Business, Energy and Industrial Strategy. And he represents the UK government at the International Energy Agency Hydrogen. I guess that's a working group, and also a meetings of energy system modelers as well. So Paul's got a wealth of experience, not only in research, but also in that bridge between research and policy. So I'm very much looking forward to what Paul has got to say. And please, as we go along, do ask questions. There's a Q&A button at the bottom of the screen where you can put them in. And apparently you can also vote for other people's questions if you particularly like them and want them to be pushed to the top of the list. Paul will speak for about 40 minutes or so, and then we'll have time for questions before we close at 2 o'clock. So without further ado, over to you, Paul, to give us your inaugural lecture.
Thank you very much, Jim, and thank you to everybody for joining. So I want to start off with a slightly pessimistic note, with some graphs that are quite hard to read, so I'm sorry about that, but I'll explain what I want you to know in a second. And this is from several integrated assessment models that are used to inform the IPCC. So this is from the SSP database that's used for the IPCC. And several of those models tell us we've already lost the race to limit global warming to 1.5 degrees C. They simply can't find a solution that keeps your temperature below 1.5 degrees C without overshooting. And even the models that can have very, very high carbon price in order to do so. So you can see on the top left, the bottom left, and the top right, there's some very expensive, not very large numbers here, $3,000, $10,000 per ton of CO2 in order to keep to 1.5 degrees. So in some ways, energy models can be quite pessimistic, but they're important because they do give us an idea about how we can decarbonize our economies and meet net zero and try to prevent climate change from happening going forwards. And for that reason, national policy, never mind the futures of our children, are based on insights from such models. So here I have a list of reports that have been informed by insights from energy system models. And these reports here are government reports, UK government reports. They go from the Energy White Paper in 2003 through to the paper in 2007, the creation of the Climate Change Committee in 2008 and their budgets. And then more recently on to the Clean Growth Strategy, the CCC's net zero report, and the net zero strategy that they published in autumn last year. All of those were informed to some degree by energy system optimization models, actually, not just energy systems. There's a lot of different types of energy system models, but particularly by energy system cost optimization models. The first few, UK Markile has had quite a prominent role in that. That was one that was developed initially for the UK government and then taken over by the UK Energy Research Centre and greatly changed. And several versions were produced for that. More recently, that model was superseded by the UK Times model, which has a similar paradigm, but a more flexible and more powerful modelling system, the Times system. And it does a similar thing. And that's, all of these models are used to produce long-term scenarios, and we use them to understand how we might decarbonize the economy. In the meantime, certainly at UCL, we also adopted other types of energy system models on different scales. So we use a global model, the TMUCL, which links energy to temperature rise, and we use European models. But they all have similar ends, essentially. And it's about working out what targets we need, building an evidence base, helping to use these models to build political consensus, developing legislative frameworks and targets, and then thinking about how we might implement decarbonisation measures. And that's thinking very much about how we respond to climate change at home, about mitigation. But of course, there's also other things we need to do. We need to think about, should we think about diplomacy abroad? We think about innovation for economic growth. We think about adaptation, particularly if we think that mitigation isn't going to work abroad. And some people like to stick their head in the sand and pretend climate change doesn't exist and won't happen. But we need to think about how we respond to climate change, and energy models are part of that. And they're part of it because we need to ensure that we have the right information to inform the sorts of changes that we need to make in our lives in order to prevent climate change, serious climate change. So here I have an example scenario. This is from the Net Zero Strategy from BEIS last year, a high resource scenario, which essentially has a lot of natural gas being used to produce hydrogen and a lower level of electrification than other scenarios. And that says we're going to partly use hydrogen. That suggests in this scenario that we could partly use hydrogen and partly use electricity to transform our energy system in the future. But we still have a large role for some fossil fuels, particularly natural gas. We need, as householders on a personal level, we need to think about how we change our lifestyles to respond to climate change. So, for example, one of the main technologies that have been identified to decarbonize heating is heat pumps. Here's a picture of a heat pump in somebody's house. And as you can see, it's quite big. And it takes a fairly large cupboard in order to install it. And that's the sort of trade-offs that individuals need to make across the country, across the world, in order to reduce emissions. And we all need to know that what we're doing actually adds up as a coherent whole in order to meet the challenges of reducing emissions and stopping climate change. So I want to explore how energy system models are built and used, and to what extent we can actually trust them. So I'm going to do it in 3 parts. First of all, I'm going to talk about the strengths and weaknesses of models. Secondly, I'm going to talk about how they're used in policymaking, quite briefly, because I don't use them in policymaking myself. And so to a certain extent, that's hearsay. And then thirdly, I'm going to give my views on what I think the future developments for these types of models is going to be. Let's start off with the strengths and the weaknesses of energy system models. I mean, the main strength is that they give us a coherent pathway to decarbonize the entire energy system. So they consider all of the flows within the energy system. So the starting point of these models is like a snapshot of the entire energy system in a particular year. We take all of the flows from energy statistics. We then project how the demands, work out what the demands are for energy services, project those forwards, and then work out what technologies we might use to meet those demands in the future while decarbonizing the system at the same time. We also think outside the energy system a little bit, particularly in recent years. So some models, for example, UK Times, we've extended so it covers non-energy emissions, and that enables us to look at the full decarbonization pathway for all greenhouse gases. And that, of course, means that we also need to think about what options there are to decarbonize non-energy emissions, such as those from agriculture, nitrous oxide and methane in particular. Energy system models are really useful because they consider links across sectors of the economy, whether you're thinking about transport, buildings, agriculture, or whatever it might be. And they consider links between technologies and commodities. So where you're using commodities in several sectors, where, for example, you might use technologies across sectors. They help you to identify what the key technologies are, and they help you to understand the implications of decisions made in one sector across the whole energy system, the whole economy. And that's really valuable. And they also help us by putting a price on the cost of mitigating climate change. So here, for example, is a global scenario, in this case, an overshoot scenario where we do very little for the next 20 or 30 years, and then we panic and invest in very large numbers of negative emission technologies in order to bring the global temperature goes up to 1.9 degrees, and then we bring it back down to 1.5 by the end of the century. And what we find is that's actually a very expensive scenario, and it's much cheaper to, I haven't shown it here, but it's much cheaper to decarbonize in the first place. But particularly those areas that are straightforward to decarbonize. They're trying to rescue the situation afterwards in the second half of the century. And we can get that type of information out of those models. And you see that there's some very big numbers here. So this is the global energy system cost in billions of dollars per year. And actually you're talking 30, 40, 50 trillion in some years. It's quite huge. And we need to keep that in mind. Another strength of energy system models is that they might help us to identify decarbonization options, which haven't been considered previously. So I have a couple of examples here. One shown in this diagram is from the ETI, using their ESME energy system model, where they had hydrogen generation, they had salt cavern storage for hydrogen, and they had hydrogen production plants. And what they noticed was that the system was investing in a combined kind of technology, which had a small hydrogen production plant producing hydrogen from natural gas. That hydrogen was stored in a salt cavern, in a large salt cavern underneath the plant. And then beside the plant, they had a large hydrogen turbine, which was used for flexible generation at times of peak demand. And that system turned out within the model to be quite a cheap way of doing things, because the small hydrogen production plant had a high capacity factor. It was used quite a lot because it was quite small. But when you needed a large amount of electricity, you had a large turbine to produce that. And it's actually very difficult to decarbonize flexible generation, flexible electricity generation. You essentially have a choice of turbines or batteries or other types of energy storage. And it makes sense to have at least some turbines in the system. Another example is the role of negative emission technologies. So when we first started looking at net zero scenarios a few years ago in UK Times, we found the model could actually meet net zero, but essentially it did the same decarbonization pathway. It was an 80% decarbonization pathway, and then had lots and lots of net zero emissions in order to balance off all of the remaining emissions in the system. And so that made us think about a couple of things. First of all, are the net zero emissions in the model plausible? Secondly, are there other technologies that we should consider for net zero? Sorry. For example, direct air capture, afforestation, soil management, enhanced weathering, ocean fertilization. Most of these are outside the energy system, but they're still important potentially. And thirdly, are there other areas that we should consider for decarbonizing that just aren't in the model because we've never considered them before? But actually, there are opportunities, and those opportunities start to make sense when you go to net zero rather than 80%, an 80% target. So as an example, I want to talk a little bit about hydrogen as an example of some of the issues with models. So I put the question to you, why didn't energy system models tell us that hydrogen was going to be the solution to many net zero challenges? Because in the last couple of years, hydrogen has received a huge amount of hype as the solution to heavy duty vehicles, to industry, and maybe to electricity, and maybe in other sectors too. And there's some very large international consortiums are building up around using hydrogen, and a lot of moves internationally on it. So where does this all come from? Why didn't models tell us this was going to happen? Well, one reason is that hydrogen has long been touted as a low carbon fuel for transport, for road transport. And studies have shown, studies going back 10 years, I remember I published a paper in 2014 on the costs of various low carbon technologies for transport. And we found that costs would be pretty similar for batteries or for fuel cell vehicles. But in the meantime, batteries have received huge investment. Automotive manufacturers, OEMs in particular, have focused on batteries more than fuel cells, and a large number of models have been released. And so particularly for light duty transport, batteries, the performance of batteries improved, and battery vehicles have taken quite a decisive lead, you would say, in terms of actually picking up market share. And that's shown by this graph, which shows new UK car registrations. The blue line shows the number of batteries. And if you'd asked me in 2019 whether batteries had cornered the market or whether it was still open for fuel cells, well, I mean, I'd have said it wasn't at all clear that batteries had cornered the market for low carbon technologies, because we could see that there was a reasonable level of plug-in hybrids and hybrid vehicles, but very few pure battery vehicles. Now, interestingly, that's changed. And in the last 2 years, although the number of cars that were sold in the UK really reduced during COVID, particularly in 2020, 2021, the number of low carbon alternatively fueled vehicles, so electric powertrains, actually increased in that time, and went up to about 20% of the total of new car registrations, and about 8% of all those cars were battery vehicles. So suddenly we have seen in the last year, 18 months or so, that batteries really have taken off. I'll be interested to see how this compares with the most recent year, to 21-22, when the statistics come out in April. And so at the moment, hydrogen is only really considered as an appropriate option for heavy-duty vehicles. It's not really being considered, at least in the UK, for light-duty vehicles. And remember that many energy system models have mainly focused on transport capacity. And many models haven't considered hydrogen for heating, industry, or electricity generation. So I remember I published this paper in 2014, Conversion of the Gas System to Transport Hydrogen, which I often tell people was the first paper to introduce the current interest in using hydrogen for heating in the UK. I remember I published that, and I organised a workshop in 2012. Since then, lots of people have done a lot of really great work on this area and taken it on. I mean, I would say I didn't come up with the original idea myself, or at least I came up with it independently, but subsequently I found it in the first version of the UK Markov model. Hydrogen was available as an option for heating in the UK. It was then taken out in a more recent version in about 2005. So it was even within our UK energy system models at one point. And I believe there was a DTI report in the mid-90s about using hydrogen for heating. But again, this was all forgotten, and then we've relearned about it in the most recent years. Within our models, we've generally had to make very broad assumptions in some areas because we don't have evidence about how you can use hydrogen in these sectors. So, for example, in industry, we assume that hydrogen can replace natural gas with the same capital costs and efficiencies as a first basic assumption. But now we also start thinking about hydrogen-specific technologies, for example, direct reduction of iron in steel making, or using hydrogen to produce high-value chemicals in the chemical industry. Similarly, I mentioned peak electricity a couple of slides ago in the ETI model, the flexible system. Now, pretty much all peak electricity generation is gas or oil or storage, and it will almost always make some sense to have some flexible turbines in our system. Now, recently we've been doing some work on a European energy system model, looking at the uses of hydrogen and trade of hydrogen. But one thing we noted when we were doing that was the carbon prices by 2050 were very, very high in order to achieve net zero across Europe. But they reduced dramatically when we introduced the option of having flexible hydrogen generation, because previously it wasn't represented there. So that tells you just how important a single technology can be in an area. And hydrogen turbines are not a particularly exotic technology. It's something we can build now. There's a few technical challenges around NOx and such like, and trying to maximize the efficiency, but more or less, they're an adaptation of existing turbines. What you really need is the kind of is the thought processes and the innovation to actually think that these might be a possibility. Maybe we should try them in the model and see what happens. And many models do have limitations for modeling hydrogen. So here I've got a couple of slides on an energy modeling study, an intercomparison study that that I co-led with the energy systems modeling community at the International Energy Agency. And this was in two parts. The first part was we asked several modeling teams to tell us what technologies, what hydrogen technologies they included in their model, so on the input side. And then the second part, we ran those models for the same broad scenario, a net zero scenario or a typical decarbonisation scenario. And we looked at how much hydrogen was actually used and where. So on the input side, this table shows you a bunch of technologies on the left-hand side, where you might use hydrogen, and it shows you which models consider those technologies and which ones don't. So we have industry as a feedstock, which is considered in 40%, hydrogen as a feedstock in industry. Hydrogen for industry decarbonisation is used in about 60% of those models, 6 out of 10. Where we extended this study for the next 4, which is why we only have some answers for some models, because not all of them replied to this. Although the ones that didn't reply, you can probably guess, don't have the technologies here in general. So we looked at direct reduced iron, producing synthetic jet fuels with hydrogen and captured CO2, producing other synthetic liquid fuels, which could be, for example, ammonia for shipping. Use of hydrogen in the dairy industry is an interesting one. Building heat and electricity generation. And you can say it's patchy. Some models include quite a few technologies. Other models include very few. Most of these are national models, but ETSAP TM is a global model, and TimesPan EU is a European model. And so this diagram shows, this table shows the outputs from that particular study. So this is for a typical decarbonisation scenario in each model. Since the models have different targets, different uses, and cover different places, we couldn't be any more specific on that. But it's still useful, I think, to look at what they show you. And I should say the uses of hydrogen in a typical decarbonisation scenario reflect the modelling assumptions in terms of what the end uses are actually included, as much as the relative benefits of the various technologies. Okay, so if you don't model electricity if you don't include hydrogen for electricity generation in your model, then it's not going to be shown in the end uses. And that's kind of what you see here. So if we look across the transport line, we see that on average, 45% of hydrogen is used in the transport sector across these models. But it varies a lot between models. So in the version of Irish Times that was used for this, for example, I think there was very few hydrogen processes represented, and it was all used in transport. In the ETSAP TM model, which again had few options for hydrogen outside of transport, then 60% is used in transport, 40% in industry. In other models, particularly UK Times, actually we only had 2% in our UK Times run used in transport. And that wasn't even in heavy duty vehicles, that was in trains and marine. In that model, we had some use for electricity, we had some used in the service sector, and we had some quite a lot used for industry. So that tells you that there's a lot of variation across models, but that variation isn't because the cost of hydrogen is different in different countries. That's just because everybody's catching up on actually using hydrogen within models. Historically, most models have had a focus on hydrogen in transport, and therefore transport is most prominent. That diagram, I think, will change in the future. If we run the same scenario in a couple of years' time, we'd find something quite different. So I want to talk a bit about weaknesses of models now, and I've already highlighted some of them in the previous slides on hydrogen. And the first big area is that the landscape can change rapidly and make your modeling assumptions obsolete. And so here's an example for renewable generation costs. On the left-hand side, in the graph from Irene, you can see how costs have reduced substantially over the last 10 years, particularly for solar and for CSP, which is a centralized solar technology. And those reductions are not always represented well in models. So the graph on the right is from a paper by Jackson Rosen and Evelina Trutnovit, my former colleague at UCL. And they looked at the projected PV cost in the future of PV systems, of solar systems. Okay. Now you'd expect that to be lower than the existing cost, because this is the future cost, and we'd expect innovation to further reduce the cost of solar. And in a number of cases it is, particularly in the 2019 publications. But if we look at the publications in 2017 and 2018, which I've put a box around, these are all actually much higher, and this is a logarithmic scale, remember that. These are much higher than the actual cost of solar is in those years. And the actual cost of solar has now come down to about about around $900 per kilowatt in 2020. And actually quite a few of these models are IPCC models. And one of the conclusions from that study was that we needed to get more models into the IPCC database, because most of the IPCC models were using oldish data, and most of the models that were using more up-to-date data weren't part of that database, and that's important. I mean, more generally, we've also had a move. If those who remember the debates back in the mid-2000s will remember, initially we were going to have a 60% reduction in greenhouse gas emissions. And then at the last minute, when the Climate Change Committee bill was being put together, that was changed to 80% in Parliament. And then since 2019, we've moved to 100%. And actually that move to a net zero target can change your mindset in terms of how you set up models. So previously with 80%, we knew that there was a number of areas that are just really hard and expensive to decarbonize. And generally people in many cases, don't even put options in for them. So for example, aviation, because the options aren't very clear. Well, once you get to a net zero target, you have a change of mindset. So you go from thinking, how can I what technologies can I use to decarbonize the system, to saying what does and doesn't, what is every single emission in my system, and is there any possibility of decarbonizing it? How can I do that? So it's a slightly different mindset. Instead of asking what isn't going to be decarbonized, you're asking, how can I decarbonize everything? And that makes previous assumptions obsolete. And in fact, we've added quite a lot of new decarbonization technologies into our UK Times model, and we continue to do so in order to have cleverer methods of meeting net zero that involves fewer negative emissions and more actual technologies, where those technologies appear to be plausible. And as part of that, I would say that the options that you actually put in these models are limited by the imagination of the modeler. So there's potential for groupthink. So somebody puts the technology in the model, everyone thinks, well, that's a good idea, and they go and put that same technology into the model as well. So I'm not sure always if that can happen as a whole community to some extent. Is there a lack of introspection that we should worry about? And do modelers understand enough of the science and the engineering of the various options in order to appraise new options and technologies and what their potential contribution might be going forwards? As an example, a few years ago, I attended a meeting which was reviewing work on decarbonizing heating. And two options that were considered in the study that we were reviewing were hydrogen boilers and natural gas fueled hybrid boilers. Now, in that study, hybrid boilers were found to be particularly valuable. And so the model concluded that there was going to be only a small role for hydrogen. But what they hadn't considered, as I pointed out in that meeting, was that you could quite just as easily build a hydrogen fueled hybrid boiler, which would use hydrogen and would have even lower emissions. And so actually they went away and did that, and then they found, and that suddenly hydrogen had a role after all. So, so that was quite a turnaround, and that was really just a lack of imagination, I think, about what the options might be going forwards. Another weakness of these models is that they try to minimize the cost of the whole energy system. And so what you tend to get out whenever you decarbonize your system is that the cost is going to be higher because you're putting additional constraints on. You're not letting the model emit CO2, and the cost is always going to be higher when you do that. And actually, perhaps we should be focusing on the economics. From an economics perspective, we should be adopting a cost-benefit analysis approach. So we should compare the cost of avoiding climate change against the cost of climate change actually happening. And the cost of avoiding climate change means the cost of reducing emissions, plus the cost of adaptation, which you'd hope would be low, plus the cost of any damage from climate change, which you'd also hope would be low, plus you're going to have some subtracting any high co-benefits that you have. Any co-benefits, for example, for better health. And we need to compare that with the cost of climate change, where you have high adaptation costs and high damage costs. More generally, many of the political aspects of energy are not really well represented by models. So if we look at the energy trilemma, we only really look at sustainability and emissions. We don't look at security of supply and affordability and price. More generally, we don't look at geopolitics of the energy transformation. So for example, here's a recent report from IRENA, which looked at the geopolitics of hydrogen. Now we have a number of countries that rely on producing and selling fossil fuels for their economies. And they're not going to be overly happy to lose all of that business. And even at low level, and the cost of, or they would be willing to produce fossil fuels at a very low price because they can still make money that way and still support their economies that way. So understanding how we transition from fossil fuels is really challenging in the real world. More generally, energy system models don't really reproduce historical trends very well, particularly when they're affected by politics. So for example, if I was to model the 1980s and 1990s in the UK, I might not pick up the dash for gas in my model because that was partly underpinned by the then government trying to undermine coal miner strikes and move the economy away from coal to a certain extent. Moreover, these types of models, they're not really ideal for understanding near-term policy options and for understanding the impacts of policies. So they can tell you where you might want to cut, but they don't really tell you how to do it exactly. And so on the subject of policy, let's think a little bit about how we've used energy system models for policy development. So governments have used these models primarily to create credible, self-consistent decarbonisation pathways. So for example, the UK government produced a number of scenarios in the net zero strategy and the clean growth strategy reports to illustrate how the UK might move to a net zero economy. The Scottish government has similarly used the Scottish Times model to produce, to understand decarbonisation pathways in Scotland. So having credible, self-consistent pathways which look economically viable is vital to actually get politicians to sign on to decarbonisation policies. And that brings me on to my second use, which is possibly the most important use historically of these models by governments, which is communication with stakeholders. And those stakeholders are both internal and external to the governments. So as an example, the UK government in both the clean growth strategy and in the net zero strategy, they represent three key scenarios, which are different views of how the UK economy might decarbonise. And in fact, in both cases, one of them has high levels of electrification. The second one has much higher levels, low levels of electrification and high levels of hydrogen. And the third one has very high levels of negative emission technologies and less decarbonisation in other sectors. Okay, so although one report was in 2017, the second was in 2021, the broad focus of those scenarios hasn't changed. The names have a bit, but the broad focus hasn't. And in each case, a few sensitivity studies were carried out for each scenarios, but there was essentially three scenarios to keep in order to restrict the number of scenarios and make the insights from those scenarios accessible. So if I go out and present 20 different scenarios, then people have a lot of trouble understanding those. But three is a nice, easy number for people to understand. Something similar happened in Scotland. So when Scotland first adopted net zero, that was partly based on insights from the Scottish Times model, which was taken to the cabinet level. And the Scottish cabinet wanted to understand that the decarbonisation pathway they were signing up to was feasible. And they wanted to have some ideas that it wouldn't cost the earth. And the model gave, the scenario from the model gave them that comfort in order to sign on to that strategy. So that was really important, that communication. And that means internally there is a lot of focus on how the governments, what the implications of the scenarios are within government. And so there's a lot of iterative development of these scenarios. There's only 3 scenarios, but there's a lot of time spent on them. People will pore over the results. Sector experts will pore over the results. They'll say, we think that looks sensible. We think this doesn't look feasible. And then they'll go back and they will edit the model accordingly, iterate a new version of the scenario, and that will keep going until everybody's happy with it. And that's a second area where communication is really important. And that's between specialist teams, particularly within government and particularly across government departments. So this type of scenario development, using this type of model, underpins joined up policy across departments. Another area that government have used these types of models is for exploring innovation opportunities. And that's generally to say this is the size of the market or the potential future market. Therefore, this is the sort of money we need to put into innovation, and therefore this is what we might get out of it from the model. So it's a little bit sketchy, but it gives you some idea. I've got a couple of examples here. One's an energy innovation needs assessment published by BEIS, which used the ESME model. ESME was designed for this type of thing, to understand technology, potential technology use in the future. On the right-hand side, I have one for hydrogen fuel cells, which I wrote, or I edited with a number of colleagues, to look at clean growth. But both had the same idea, essentially looking at the size of future markets. But I think there's a question about whether we can do this type of, whether we should do this type of study globally. So these are very inward focused, UK focused. But really, when you think about innovation, you need to think what's happening elsewhere. So are you going to avoid imports through innovation? Are you going to build an export economy? And that's something maybe we need to think about in the future. One issue with the use of energy system models by governments, to my mind, is the very limited use of uncertainty studies. So the types of uncertainty that governments tend to use, they tend to be limited to doing a sensitivity study. So if there's a small number of factors that stakeholders think are important, that the modelers think will have an impact on the energy system, then those will be examined in derivatives of the main scenarios. Yet the uncertainty can be very large in the scenarios, and there can be a large number of options. So here I have a graph from my colleague, James Price, which looks at suboptimal energy system modeling. So what happens if the energy system, the cost of your energy system is, say, within 1% of the optimal cost? How different can it be? And the answer is, in some circumstances, it's going to be quite different. And we can see that there's a large disparity in coal use. I should say this is a global study. So this is using a global energy system model, not the UK model. And this is looking in 2050. And there's large differences in coal use in particular, but also in gas use, in oil use, in nuclear use, across the various scenarios. And so I do wonder the extent to which we have a really good understanding, even at UK level, of all of the potential energy system decarbonisation routes that are available. So I'm going to move on to the third part, which is on future developments on the horizon. And I want to talk about three areas. First of all, technical improvements to models. Secondly, improving how we actually use the models. And then thirdly, taking a more professional approach to modeling. And some of these Picking up points I've made a bit earlier. So I think we need greater imagination on future demands and options. So for example, here are some pictures from Airbus of their zero-E planes, which use hydrogen, which are designed to use hydrogen. So this is a program that Airbus are working on at the moment to use liquid hydrogen in aeroplanes as opposed to jet fuel. And this would be for medium range, not long range aeroplanes. One issue is that they take a rather large part of the fuselage to store the hydrogen, which is why the whole back of the plane, the whole coloured in bit at the back is hydrogen essentially. So you don't get as many people in them, and that's an issue. And that's one reason why that they are medium range. Other people are looking at using ammonia for medium range, up to 3,500 kilometers. And people are starting to look at electric or battery-powered flights for short range, up to a few hundred kilometers. So there are technological options to decarbonize flying. Even for long range, you can produce synthetic jet fuel from biomass. You can produce it from hydrogen and captured CO2 in a much lower carbon way than existing jet fuel. And when people are starting to include those in models. So we have a PhD student at UCL who's added jet fuel into the models. And actually in a net zero scenario, it absolutely makes economic sense to use synthetic jet fuel rather than trying to rely on very high net zero emissions. And this brings a more general point that these types of models are really inherently conservative. So we often assume that the future is going to be a kind of an extension of the past. So we take our energy service demands, for example. We start with a snapshot of the year in a particular year in the past. We work out what we think the demands are in that year, and then we project those demands forward. So we say this is how we think they're going to change. And often we do that using econometric studies. And then when we try and work out how we're going to decarbonize the system going forwards, we do this using current technologies rather than technologies that we might develop in the future in many cases. Now, that's arguably good in some ways because we're applying the precautionary principle of only relying on things that we understand. But it's also not likely to be accurate. And also on the demand side, it overlooks the opportunity to shape more sustainable demands in the future. Now, I do have some colleagues in the CRED consortium who are looking at low energy demand scenarios. But we also need to think about more general lifestyle changes. So, for example, how housing patterns are changing over, how housing in the UK, the use of housing in the UK is changing over time, for example. What the impacts of driverless cars will be on demand if suddenly there's an affordable option for the very young and the very old who can't currently drive. How can we best integrate social preferences of people into economic models? Is a real challenge, I think, that nobody's ever really cracked. You could do it through some sort of multi-criteria analysis. And certainly a weakness in previous projects that I've been involved in was that we planned integration phases at the end. And in fact, we found that you could only coherently integrate those types of social preferences into models if you planned it from the outset. You planned your social studies and your modeling studies for that integration from the outset. We could use alternative approaches to identify technologies. So instead of looking around and saying, what are people working on, what's available, you can also try to systematically identify all possibilities to reduce each greenhouse gas emission across the economy. You can look for low carbon alternatives to every high carbon fuel and process in the economy and say, what can you do? So, if I have various types of petroleum products, which of these can I make out of biomass and how, and what are the implications, for example? But as an ongoing thing, I think it's also important that models have a close link to engineers who are designing new technologies in order to understand the possibilities for new technologies. I think we can improve boundary condition assumptions in a number of ways. So here's an example where we were going for biomass, where we were going from a global model to look at global trade to a UK model to look at the role of biomass in the energy system. And then that was being informed by a high-resolution UK model of high-resolution UK bioenergy model, BVCM, bioenergy value chains model. And the BVCM was informed by a really high-resolution model of UK biomass resources. Okay, so you can see lots of different scales going on in order to understand the potential for biomass in the UK energy system. And that's something I think we need to try and do more of in the future. This is just about biomass, but more generally, we need to think about land use models and how we can link land use models with energy models, particularly on a national scale. So it happens on a global scale, but not really on a national scale, because we need to think about farming and multiple uses of land, or making sure we don't use the same land for different energy system services. So that's important. We also need to think about, if we want to think about innovation and trade and the dynamics of commodities, including things like not just the availability, for example, for biomass, but price variations, for example, for electricity that's traded between different countries. And we also need to think about linking national models to global models. So I think that's something that we're going to see more of in the future. Another potential opportunity that's coming around is better quality data in order to justify how we build energy system models. And also, I hope to enable us to start thinking about local energy system modeling to inform local decision making in the future. So we're now seeing the development of really high resolution models on an individual building scale, and also looking at each floor of the building, different uses in different floors of the buildings. We call these 3D stock models, and they're being developed by the Energy and Buildings team in UCL. And we could aggregate data from these types of building models and similar transport models to understand how local energy systems function, and then inform local decarbonisation plans. The second area I wanted to talk about was improving how we use models. And the first part is thinking about building a coherent ecosystem of energy models. So when we use energy models in decarbonisation assessments, we don't tend to just use energy system models, and it wouldn't be appropriate to do so. We have some high resolution models, often stock models, so for buildings, industry, transport, probably all separate models that have a really detailed representation of different parts of each sector. Now we have electricity models that work at very high resolution, that consider electricity system balancing, and we have interactions between these. But as things stand, these models aren't designed to interact together at the moment, and I think something going forward is to think about how we might do that in a coherent way. I mean, certainly what I found is that linking models is quite easy, but linking them in a way that makes sense is really quite challenging. And it's not feasible to build a model of everything that would tell you the answers that you need to know, not least because of the breadth of the model, you wouldn't be able to have the spatial and temporal resolution that you require, and that they use different paradigms. You'd want to use different paradigms and different models anyway. So I think we need to think carefully about how we link models in the future. I think we need to think about how we do joined up uncertainty studies. So I mentioned the limits on uncertainty studies in most government circumstances. Now, sometimes uncertainty studies do extend to looking at parametric uncertainty using Monte Carlo. Lots of other methods of uncertainty have been tested as one-offs by academics. So I mentioned the one looking at near optimal solutions, and there's a number of different methods such as stochastic optimization that you might use, as demonstrated by this diagram. But what I don't think is what I've never seen is a substantive uncertainty study that's been carried out for a single version of a model that explores different aspects of uncertainty using different methods in a coherent way. I think that would be really valuable. Oops. And in some cases, it would be better not to use energy system models at all. So these are graphs from my colleague Neil Strachan and his team, and they're designed to look at policy implementation. And energy system models don't give you great insights on short-term policy options, not least because they don't consider the range of population groups that you have in a country, so going from very poor to very rich. And they tend to assume, energy models, system models tend to assume you have a very happy world in which people don't try and cheat the system. Whereas if you're developing a policy and you spend 90% of your time understanding how people might cheat it and then try and stop them. such as Kashmir ash in Northern Ireland. Finally, on professionalism, there's a strong move towards open source modeling. I think that's really important. Joe DeCarolis argued in a paper that most papers that use energy system models are not scientific, because the work that they do isn't repeatable if the model isn't available. And having fully open source models enables repeatability. As shown in this quote on the left-hand side from a recent Horizon Europe call, that their funding now requires new model updates to be published openly. But for many academics, publishing models gives away IP and potentially undermines future funding for their model development and the use of the model by creating competition with the community. So there isn't really much of the incentives for academics to share models is not great, and certainly hasn't been in the past. Now, in our case for UK Times, we have an expert user group with 20 institutional members. We welcome others to join and use the model if they want to. But actually, we haven't published the model yet, and we do plan to. So we are producing a new version of it, a multi-regional version, which we plan to make fully open on a website that you'll be able to download. There's two reasons we haven't published the model yet. One is that the backing spreadsheets are poorly organized, so they don't look desperately professional. And the other one is that they contain confidential information in some cases. And we're now making an effort to remove any confidential information in the new version of the model. So that's one way, one area of professionalism. Another, I think that's important, is quality assurance. And we saw at the start of the pandemic, where modeling behind, you can see that the headline on the left-hand side, modeling behind lockdown was an unreliable, buggy mess, claim experts. This is from the Daily Telegraph about Neil Ferguson's work at Imperial. And essentially it said that the code was an absolute mess and shouldn't have been used. Underneath the comment, Imperial's programming could go down as the most devastating software mistake of all time. On the right-hand side, you have an earlier example where the government got its sums wrong on the West Coast rail route bids and suspended some civil servants because the contract was given out in a way it shouldn't have been. Okay.
Well, could you just draw it to a conclusion, just so we can fit a couple of questions in, if that's all right? Thank you.
Absolutely, just about there. I think I have one more slide. I will just say that the government review led to a quality assurance approach for models being developed, and that the calculations on the right-hand side were actually seem to be flat. So all was well that ended well. And I think I have the pleasure of working with experts from a number of research centres on a climate change project. And the UK has developed a network of research centres that work closely with the Met Office to develop really sophisticated Earth system models. And I'm kind of quite jealous of that. These centres coordinate model development, and they do it in a really professional way. They have a permanent staff that specialise in software development and management, and that's underpinned by reliable long-term funding. And so they provide a focus for the wider academia to use those models to help improve those models, but they provide the basic model services and make sure that everything's done in a really professional way. And nothing similar really exists for energy system modeling. Now, UK Times wouldn't exist without the UK Energy Research Centre, and UK does some great research, but it's not funded with resources for ongoing maintenance of models. It's not designed to do that. It's designed to publish papers. It's a virtual centre. The Energy Systems Catapult doesn't have a role in community building for modelling, although it has picked up many of the models from the ETI when the ETI came to an end, such as ESME. And when I look at UK Times, I see I have a model that's used by 20 stakeholders. It has a community. We really need a model gatekeeper who's interested in energy systems, interested in model design, understands programming and quality assurance, and is a little bit obsessive maybe about all of these, but is more interested in building communities and helping users rather than publish papers. And that means that these types of models don't fit well in academia. And so kind of my closing argument here is that maybe I shouldn't have been doing this for the last 10 years, and maybe UCL shouldn't be looking after these types of models. maybe we should think about what the economic consequences are of making good or bad energy investment decisions as a result of high quality or poor quality information from these models. Because I don't think anyone's really thought about that. But if those consequences are pretty substantial, then maybe we should think about how we can plan for the long-term maintenance of such models that we use to provide those information. And think about funding approaches that give the right incentives and that underpin that type of long-term maintenance, because I don't think we have them at the moment, and I think that's an issue for the UK. So essentially, to answer the question, what has energy system modeling ever done for us? I mean, it's certainly been a platform for communication of difficult issues. We can improve how we decide what to include in models, how we link models, how we understand uncertainty, and how we ensure that models are developed professionally. But overall, I think these types of models have produced evidence for the public and politicians, and have given people the confidence that decarbonisation is feasible and economically viable. And so they have had a really important role over the last 15 years or so in our policy processes in getting where we are today. So thank you very much for listening, and apologies for going a bit over there, Jim, but happy to take some questions.
Thank you very much, Paul. You'll have to imagine the round of applause that no doubt you'd get if everybody was in the room. We have 140 odd people on the Zoom at the moment, so just imagine them all clapping to themselves. But thank you very much. That was fascinating, particularly your reflections about the role of modelers as well as the models themselves. I think that was really well taken, and your point about at the end about who actually should be paying for the curation of this capability. Wherever it may lie. I'm going to do a very quick fire thing with some of the questions, because we only have a couple of minutes left of our scheduled time. All I'd suggest is, if Paul, if you've got time, that you could answer any of the others offline, and I'm sure Velvet and the comms team might be able to put the answers in touch with the questioner so that people get their questions answered offline. So, perhaps you could do some brief answers. And I've got one, although the order's just changed. So how much behavior change is assumed in the models, which is quite a popular question about models. How do they deal with behavior change?
Very little in most. So we do, some models consider elastic demands. So as prices go up compared to some sort of baseline, we assume due to decarbonisation, then we assume that demands will go down a bit. But some people have done some testing with mode shifting, particularly for transport. So saying what happens if people start walking and cycling more on demands, and also trying to put that within models, so trying to monetize it essentially in order to put a price on it, so you can optimize it, cost optimize it. But in general, there hasn't been a great amount. And where we do consider behavior change, it tends to be an assumption, an external assumption that we put onto the demands in the model.
Thanks. I'm going to take a couple more, but bear with me, everybody, if I overrun by a couple of minutes, but just so we can squeeze a couple more in. One from Edward here. You mentioned hydrogen technologies being underrepresented in several models through your lecture, but what other technologies do you think are currently overlooked by most models?
That is a good question. Certainly, so I think I mentioned a number of them actually. So I think international aviation and shipping. I mean, I really think actually, the more I look at aviation, the more I think it is actually possible to decarbonize it. I mean, it's not super cheap, but then most of the people who take aviation or do a lot of aviation are not super poor. So I think I can see feasible routes for it. Shipping as well, and there are fuels that are available, such as ammonia, and I can see an international ammonia trade building and being used to decarbonize shipping, if the right incentives were in place, or penalties on ship owners, because international jurisdictions make that more difficult. I think there might be a lot of options on land use, on negative emissions, and on reducing agricultural emissions that we don't really consider. Going back to the energy system, I think there might be quite a lot of biological options, biomass type options for petroleum fuels. Essentially, in a lot of areas, we assume that you just can't decarbonize petroleum fuels. And that's probably more because we haven't thought about it a great deal for the more exotic types of fuels. So where we have chemicals in the system, carbon-based chemicals, we might well be able to produce versions that we don't consider at the moment. And I think that would be a nice area to think about in the future.
Thank you. And something I was dying to ask when you put, I think it was your first slide, what is the $3,000 a ton technology that you'd shown there, and what technology would kick in at 3,000 but not at 1,000? Just can you unpack what's going on there?
It's a really good question. I'm not sure, to be honest. I mean, my guess is that you're moving into really expensive land use. So decarbonizing cattle emissions, for example, methane from cattle, or nitrous oxide emissions from crops. That would be my best guess, because that's the sort of areas you tend to start getting into the thousands once you get beyond a small number of cheap or free or technologies that actually save you money. You start getting to really high costs, but that's a guess.
Right. And I think a final one, because of time, and again, I'm sure, Paul, you're willing to answer others afterwards. And it relates to something you touched on, which is whether energy system models can link to economic models to explain the economic opportunities from the transition to net zero, but also thinking about who pays, which is obviously a very politically salient question at the moment. So can the models deal with those sorts of questions? So
yes, in theory they can. So a number of people have looked at linking economic models. Well, okay, so maybe two parts. So the first thing that we have looked at within energy system models, within the Mark on the Times models, is using a basic macroeconomic, is implementing a basic general equilibrium macroeconomic model, which links decarbonisation to economic growth, and so answers the question: if we decarbonise, what will be the impact on economic growth going forwards? So we've done that within the time modelling framework. External to the framework, a lot of people have started dabbling with linking energy system models to CG models, computable general equilibrium models, in order to understand the economic impacts across the economy. And there's a number. This is a little bit like the linking to the other models I talked about, where it's quite easy to link in some ways, but trying to do it coherently is quite hard. So I'm currently doing a project on overshoot pathways, global modeling of overshoot pathways, which is the one I'm working on with the various NERC centers. And one thing we're trying to do in that is a cost-benefit analysis of climate change, which I talked about. And we're going to try and do that by linking together the energy system model, a damage costs model, and a CG model, a global CG model together. Okay. Now, we don't know if it's going to work or how well it's going to work. We tried once before and it worked a bit, but we weren't entirely happy with what we got. And so it's something that it's on the edge of our capabilities. It's something we're working on, but it's very much in the academic sphere at the moment. Thank you, Paul. Yeah, I'm sure that will develop further in the coming years. And final question, which I'm going to ask you for a one-word answer to: blue hydrogen or green hydrogen? Somebody has asked. Depends when, where, and for what. Both. Very good. That's a good one-word answer. Thank you, Paul, for being game on that one. That's not an easy question to answer. And thanks once again, and apologies to those that haven't had their questions answered. As I think Velvet's just put in the chat, we will endeavour to follow up with you. Lots of great questions, which shows you've had a really good engaged audience, 100 of whom are still with us. So thank you very much, everybody, for joining us. But most of all, thanks to you, Paul, for a really fascinating talk. I think not just presenting a lot of graphs and scenarios, which modelling talks often do, which is great, but actually you've really reflected on the modelling process, the kind of decisions modelers have to make, some of the some of the things that they can't do, which they wish they could do, but also thinking about how you might improve the transparency of models and the results and what they look at as well. So lots of things for us all to think about. And thanks once again for doing it. And apologies we can't now celebrate with a drink afterwards, but I'm sure we'll do that in due course once we're all together in person again. So thank you once again, Paul, and thanks everybody for joining, and enjoy the rest of your day. Bye for now. Thank you, Jim. Thanks, everybody.